central limit theorem. In this lecture, we will talk about central limit theorem. This is one of the most remarkable result in probability theory, and it has theoretical importance as well as a lot of applications in different areas of science, engineering and social sciences. So, we will recall what we have discussed so far. We are interested to find out the behavior of Sn by n, that is the sample average, as n tends to infinity. So, this is our goal, and in the last class we discussed about two important results, that is WLL n and SL. So, weak law of large number and strong law of large number, they say about the behavior of Sn by n as n tends to infinity. So, let us consider the special case, that is, suppose Xn to be sequence of independent and identically distributed random variables is with mean mu and variance sigma square. Now, according to weak law of large number, Sn by n converges to mu in probability, that is weak law of large number, and strong law of large number similarly it converges on almost 0 to mu in this case, because it is IID. Our goal is what is the distribution of Sn, but it says that Sn by n as n tends to infinity, it converges to a fixed quantity mu. But is there any deviation from that mu, or how does Sn behaves when n is large? So, it will be approximately equal to, suppose when n is large, because Sn by n will become mu, implies that Sn will be approximately equal to n mu. But how much deviation will be there, that we do not know from these two laws, weak law of large numbers and strong law of large numbers. Also, we know that Sn by n converges in probability to mu. Now, convergence in probability implies convergence in distribution. Therefore, Sn by n converges in distribution to mu. So, that means the distribution of Sn, so Sn will become approximately equal to n mu, and as a consequence of weak law of large number, Sn will be a fixed number. It is approximately equal to n mu, but there will be no deviation, there will be no distribution for Sn. But actually there will be, when we consider Sn, for large n, Sn will be approximately equal to, Sn is approximately equal to n mu. That means it will deviate from n mu, and now how we can find out these deviations. So, or what is the probability of any deviations. So, those type of answer we have to give, and that is of great practical importance. So, how we can proceed? So, in weak law of large numbers, we considered Sn by n. So, that is the sample average, So, sample average converges to true average, that is the law of large numbers. But in the case of central limit theorem, we will find out the asymptotic distribution of, suppose, Sn minus n mu, that is the deviation. Now, here we consider the standardized average. Unlike sample average, here we standardize the average. So, instead of dividing by n, so Sn minus n mu, anyway this is the deviation, divided by sigma we are doing, sigma into root n. So, instead of dividing by n, we are dividing by root n. So, this is equal to, we can write this is equal to that is summation xn xi minus mu I is equal to 1 to n divided by sigma into root n. So this is the quantity we are considering. Now this random variable, now Zn is a standardized random variable in the sense that E of Zn, if I find out E of Zn, then there will be here E of xi will be mu, so mu minus mu will become 0. So that way E of Zn is equal to 0. It is a 0 mean random variable. Similarly, variance of Zn will be equal to, how do I find variance of Zn is equal to E of summation xi minus mu divided by sigma into root n, I going from 1 to n whole square. So variance of Zn. Now these are independent random variable. So because of that, this variance of this sum will be equal to the sum of the individual variances. So that way we can get that this is equal to summation E of xi minus mu whole square I is equal to 1 to n divided by, because it is square, sigma square, and root n square is n, and this will become n sigma square again. So that is equal to sigma square into n divided by sigma square into n, that is equal to 1. So that means variance of Zn is equal to 1. So we are now considering the asymptotic behavior of Zn, how Zn is distributed when n is very large. So the central limit theorem gives answer to this question, what is the distribution of Zn, and there are different statements. We are considering a simple statement, the simplest case, that is the Lindeberg-Levy central limit theorem. Here we consider xn to be a sequence of IID random variables. So here we assume that xn is IID, independent and identically distributed, but that is not very critical. We need only IID condition, independent condition, but for simplicity we consider the case of IID, independent and identically distributed sequence. Now as earlier we defined Sn is equal to summation xi I is equal to 1 to n, Zn is the standardized average. So Zn is distributed as that is we have to prove that according to the central limit theorem, Zn converges in distribution to Z, where Z is normal random variable, standard normal random variable. What does it mean? N is so this Z is standard normal 0 1, that means it has mean 0 and variance 1. So that way fz of Z is equal to e to the power half of Z square divided by root over 2 pi into 1, root over 2 pi. So that this is the PDF for Z. So what we are telling that if xn is a sequence of IID random variables with mean mu and variance sigma square, which is finite of course, let Sn is the sum of the sequence and Zn is the standardized average, then Zn in distribution converges to standard normal random variable. So what does it mean? That limit of the CDF f Zn of Z, that is the CDF of Zn, that standardized average, the limit as n tends to infinity will be the CDF of standard Gaussian. So this is the standard Gaussian. If I integrate from minus infinity to z, that will be the limit of fzn of z. So that is the Lindenberg-Levy central limit theorem. We will try to prove this using moment generating function of Zn and the continuity theorem of convergence. That means if moment generating function sequence converges, then corresponding distribution functions will also converge. That is the continuity theorem we discussed earlier. Now we will prove via moment generating function. We know what is moment generating function. Moment generating function of Zn will be equal to E of expected value of e to the power s Zn. Okay, so that is equal to, same thing I can write, E of e to the power s, now Zn as I have defined, that is equal to xi minus mu divided by sigma into root n I going from 1 to n. So this is the moment generating function, and now I know that this quantity, suppose because it is exponential, we can write it as a product E of e to the power. So this is the sum is there. So here I can write a product I is equal to 1 to n e to the power s into xi minus mu divided by sigma into root n. So let me call this part xi minus sigma. Let me call this random variable as yi. Okay. So then we can write in terms of this MGF of yi, that is our goal. Okay. Now at this stage, so what we have got is that this is equal to E of product of I is equal to 1 to n e to the power s yi by root n. We can write like this, but this xi's and equivalently yi's are independent random variable. So this expectation operation I can take inside. So this will be product I going from 1 to n E of e to the power s yi by root n. Okay. So this is the moment generating function. Now this we can write as moment generating function of yi at point s divided by root n. That's why this part we can write as myi. This part that is m of yi at which point? At point s by root over n. So that way we get this expression. And since all these random variables y1, y2 up to yn, they are identically distributed, therefore this product will be, there will be only one moment generating function MGF. So we can write it as myi s by root n to the power n. So this is the result we got. So f mzn of s is equal to myi at point s by root over n to the power n. Now this yi is a zero mean unity variance random variable. Now moment generating function, because it generates the moment, that's why it is called moment generating function, and its power series expansion is given by this. This is the summation of some coefficient to the power into s to the power k divided by factorial k, and these coefficients are the moments. So that way MYIS, it is the summation of the power series. What is power series? This is s to the power k divided by factorial k with coefficient. Coefficient is given by e of yi to the power k. So for this series, first term will be always equal to e of yi to the power 0 will be always equal to 1, that is equal to 1. So it will start with 1, that means we can write it also as 1 plus summation. So summation k is equal to 1 to infinity e of yi to the power k s to the power k divided by factorial k. Now yi, what is our yi? Yi is equal to xi minus mu divided by sigma. So e of yi is equal to 0 and e of yi square will be equal to e of, that is equal to e of xi minus mu whole square divided by sigma square. So that way that will be equal to 1. So therefore this power series expansion we can write near s is equal to 0. This expression is for suppose region of convergence, but here we are particularly considering near s is equal to 0. So that we can write my I of s is as 1 is this one, plus then e of y square is equal to 1, therefore k is equal to 1, it will be 0. When k is equal to 2, now we will get this 2 s square by 2, and then this e of y square is equal to 1. And the remaining term we can write in small o s square, this notation, so that this term will go down to 0 as s tends to 0. When s tends to 0, this term will go down quickly to 0. So this is the MYI of s. Therefore our goal is to find out MZN of s. So that will be MYI of s divided by root n to the power n. So to the power n, therefore we can write as 1 plus s square by 2n, because it is s by root n. So square, when I make it square, s square by n. So that way 1 plus s square by 2n plus O of s square by root n square is n, whole to the power n. So this is the MZN of s. Now question is, what will happen as n tends to infinity? So limit of MZN of s as n tends to infinity. So this we can apply standard result, 1 plus suppose x by n to the power n limit n tends to infinity. So that will be equal to e to the power x. So that result, because this term will quickly go down to 0 as n tends to infinity, so we will have the power of 1 plus s square divided by 2n to the power n as n tends to infinity. So that will be equal to e to the power s square by 2. Now this e to the power s square by 2 is the MGF of standard Gaussian, MGF of standard Gaussian. So that Gaussian. So what does it mean? Suppose suppose if I consider e to the power s square by minus s square by 2 root over 2 pi, this is the density function, into e to the power s x dx. If I carry out this integration, then I will get this e to the power s square by 2. Moment generating function of this standard Gaussian is this. This integration is also easy. By using the property of the Gaussian itself, we can complete this integral. So what we have observed, that limit of Zn of s as n tends to infinity is equal to e to the power s square by 2, which is the MGF of standard Gaussian. So now we recall the continuity theorem. If MGF converges, then corresponding CDFs also will converge. So that way we get that limit of fzn of z as n tends to infinity will be equal to the CDF of standard Gaussian, that is given by this. So what we have established, Zn converges in distribution to the standard Gaussian. So this is the remarkable result we have proved in the case of IID case, but we have used the strong assumption that moment generating function exists, but more rigorous proof can be obtained, but we consider the simplest proof. So what is the implication of this? That Zn it is says that Zn converges to Z, which is standard Gaussian, zero mean unity variance Gaussian. So that means what is Zn? That is Sn minus n mu divided by root over n into sigma. So that is approximately normal 0 1. Okay. So therefore from this we can say that this Sn itself, when n is large, because this is Gaussian, so from that we can find out that this Sn itself will be distributed as Sn will be distributed as normal. It is normal. So what will be the mean of Sn? That is equal to n mu, and variance of Sn is n sigma square. So this is the distribution for Sn, approximate distribution. Now it is normal with mean n mu and variance n sigma square. Earlier we established that Sn is approximately equal to n mu. There is no deviation, but now we have learnt how to characterize this deviation, and that is normally distributed. Now in our derivation, that independent and identically distributed, that was the assumptions, but that need not be the case. There are different statements, and more important is that Xn should be a sequence of independent random variables. For example, there is a Lyapunov central limit theorem. So according to that, suppose this is a sequence of independent random variables. Now this is not IID, because each Xn will have different mean mu n and different variance sigma n square, and Sn you define as summation of xi as earlier, and clearly if I have to find out E of Sn, that is mu Sn, E of Sn, if I have to find out, that is equal to mu Sn is equal to summation of the individual means. So that way mu of Sn is equal to summation of mu I going from 1 to n. Similarly sigma Sn square, because of independence, it is sum of the variances, that is sigma I square I going from 1 to n. So we have a sequence of random variable, independent random variable with mu n and sigma n defined. Now suppose for some delta may be 1, 2, etc. This limiting condition is satisfied, E of xk minus mu k to the power 2 plus delta. So this is the central moment of order 2 plus delta. If we take the summation from k is equal to 1 to n and normalize by corresponding variance, sigma Sn square variance is this, that also we will consider some power 2 plus delta. If this limit, the limit of this ratio goes down to 0 as n tends to infinity, then this quantity Sn minus mu Sn is given by this divided by sigma Sn is given by this, that will be distributed as normal distribution. So this is also this is known as the Lyapunov central limit theorem. So according to that, only independence condition is required and some restriction on the moments. But essentially we have to consider a sequence of independent random variables with finite mean and variance. Then we can apply the central limit theorem. Now let us try to interpret this result. Our Sn, what we have established that Sn is approximately Gaussian with mean and mu, variance for IID case, for example, variance and sigma square. So this is the distribution of Sn. Now when it happens, when Sn is equal to, that is this Sn is equal to summation xi, I is equal to 1 to n. Sn is a summation of independent random variables, that is important. So if a random variable is a result of superposition of several independent causes, this I can consider to be causes. So Sn is a result of several independent causes. It is a superposition of several independent random variables. Then the random variable can be considered to be Gaussian, because it will be approximately Gaussian. For example, you consider the thermal noise in a conductor. Now this noise happens because of the random motion of electrons. Now there are millions of electrons in a small conductor. Now this noise voltage is result of the motion of so many electrons. So that means it is the result of superposition of the voltage generated by each electron because of the thermal motion, and their motions are independent, therefore these are independent random variable. Therefore this thermal noise, whatever thermal noise is generated in that way, that can be modeled as a Gaussian. Similarly, observation error, measurement error, etc. is always modeled as a Gaussian. So that way Gaussian plays an important role in not only in signal analysis but modeling and then filtering, etc., various applications. So that way this central limit theorem has is important in engineering, in science, in social sciences, and wherever probability is applied, central limit theorem has a role to play. So that way we have seen the central limit theorem. Now we can consider one example. Suppose number of heads in 1000 independent tossing of a fair coin. So this that means if I consider the result of one tossing of a coin, that is xi is equal to 1, suppose if a head occurs, 0 otherwise. If tail occurs, then it will become 0. So that way xi is a Bernoulli random variables. So in this case it is a fair coin. So P of xi is equal to 1, that is equal to P of xi is equal to 0 is equal to half. Now number of heads in 10,000 independent tossing of fair coin. That means Sn, in this case of course S 1000, Sn is equal to, that is summation xi, I is equal to 1 to n. So this will give the number of heads, because for single head, if it is head we will get 1. So if we count all ones, then we will get Sn, that is the number of heads. So in this case S 10,000, so that is equal to summation xi, I is equal to 1 to 10,000. Now according to weak law of large number, I know what is E of xi. E of xi, that is equal to mu is equal to E of xi, that is equal to, now xi can take two value, 1 into with probability half plus 0 with probability half, that is equal to half. Mu is equal to half. So according to weak law of large number, this S 10,000 will be approximately equal to 10,000 n, that is n, into mu, that is equal to, mu is equal to half. So this will be approximately equal to 5,000. So this is the weak law of large number. But using the weak law of large number, we cannot consider any deviation, but practically there will be deviation. We may get, clearly we may get near 5,000 heads, nearly 5,000 number of heads, but it may vary to 5,500 or 4,500, like that. How to tackle that? Now CLT gives me a way to tackle that. So suppose if I ask the question, what is the probability? So probability of getting more than, suppose 6,000 heads. So what we want to find out, what is the probability that S 1000, S 10,000, that is greater than 6,000. So this probability if I have to find out. Now I know that this S was 10,000. This is same as probability that S 10,000 minus n mu. N is here 10,000 into mu is equal to half divided by root over n. Sigma is half into root over n. Root over n is root over 10,000 is 100. So this is greater than, now same thing we have to do the right hand side also, 6,000 minus this is 5,000 divided by this is maybe 50. Okay, so this probability we have to find out. Now I know that this is standard Gaussian. So probability that this is Z. Z is standard Gaussian. So this Z is greater than, now this is 1000 divided by 50. 1000 divided by 50, that is 20. Z is greater than 20. So this quantity will be equal to, because it is a standard Gaussian, so it will be integration from 20 to infinity e to the power minus z square by 2 dz. divided by root over 2 pi. So this integral we can evaluate using the table or standard cube function type of tool, and we can evaluate this probability. So that way we can find out what is the probability that Zn or Sn will deviate from the expected value, that is 5000, by some amount. So this is the utility of the central limit theorem. For example, if I say what is the probability that this probability that Sn is greater than 5000. So we can, because 5000 is the mean, this is a standard Gaussian. So what is the this is a Gaussian. So for the Gaussian, what is the probability that the random variable is greater than the mean? So this we can apply the CLT and we can show that this is equal to half. So that way we discussed the utility of the central limit theorem. So in this lecture we covered the central limit theorem. This central limit theorem says that sum of independent random variables is approximately Gaussian. When it is large, suppose n is large, the sum of the independent random variables. So it is required that sum of independent random variables, their PDF will be, if it is a continuous random variable, all random variables concerned are continuous, then that sum will be PDF will be approximately Gaussian. For example, if we consider suppose n uniformly distributed random variables. So now in this case that means summation xi I is equal to 1 to n. So there are n uniformly distributed random variable. Now because of this sum of independent random variables, so uniformly distributed and independent, we have to write independent. So what will happen, that this sum will be always Gaussian distributed, this will be normal distributed. Okay. So normal distributed, and this, what will be the mean of this distribution? So each random variable mean we have to find out, then sum of these means will be the means of this normal distribution. Now this n can be, suppose if n binomial random variables, suppose if we consider n binomial random variables and they are independent, suppose in that case also this sum, the CDF of this sum will converge to the CDF of the Gaussian, because this is a discrete sum now, sum of discrete random variables. It cannot be a continuous random variable, but its CDF will converge to the CDF of the standard CDF of the Gaussian random variable. So that way this is the importance of the central limit theorem, that if we have independent random variables and if we get the sum, then sum will be always Gaussian distributed. So that way we have considered now three results, that is we started with laws of large number, laws of large numbers, we have weak law of large numbers. So basically we are interested how does Sn by n behaves. So if I consider Sn by n, then we have laws of large number, and then within laws of large number we have WLN and SLLN, strong law of large numbers. So these results are derived when we consider Sn by n, but to derive how this Sn, for example, is distributed as n is large, to get that answer we consider not Sn but we consider normalization. Suppose Sn minus n mu divided by root n, this is the importance, root n into sigma. So this quantity is Gaussian according to CLT. So that way in laws of large number we are interested in Sn by n. Here we consider another sequence Sn minus n mu divided by root of n. Because of that we got the Gaussian. Thank you.